All right, let's dive straight into it. The big question this paper tackles is, how can we get language models to really reason well, but without, breaking the bank on compute?
Yeah, achieving strong reasoning cost effectively. That's the goal.
And this paper introduces Tina tiny reasoning models via LoRa. It's a whole family of models designed for exactly that.
The key idea, and this is pretty neat, is applying these parameter-efficient updates, LoRa, during reinforcement learning. And they do it on a pretty small base model, only 1.5 billion parameters.
Right, and the headline result, Tina manages competitive reasoning, sometimes even better than the state-of-the-art RL models using the same base, but the cost difference is just huge.
Forget this. They saw over a 20% boost in reasoning performance and 43.33% pass at 1 on the AME 24 benchmark. That's a tough one.
And the cost for that best models post-training in Evil, $9, just $9.
Which they estimated something like a 260-fold cost saving. Pretty wild.
Their theory is that LoRaL helps the model quickly latch on to the structure or format of reasoning that gets rewarded by the RL. But critically, it does this while keeping the base model's original knowledge intact.
Makes sense. And importantly for the community, they've open-sourced everything, code, logs, weights, so people can actually build on this.
Definitely encourages reproducibility. So, okay, we've seen LMs get incredibly good lately, right? But this kind of deep, multi-step reasoning, it's still a major hurdle, isn't it?
Oh, absolutely. For complex stuff like scientific discovery or planning complex actions, you need more than just retrieving facts or summarizing text. You need that step-by-step logical deduction.
And that's proven tricky. Why is it fundamentally harder than, say, translation or summarization?
Well, it's about connecting the dots. Multi-step reasoning means linking different pieces of information, understanding the logic between them, inferring new things. It's not just pattern matching, it's synthesis.
So how have people typically tried to teach models this? I know supervised fine-tuning, SFT, is common. How does that stack up against reinforcement learning, RL, for this task?
Right. SFT relies on showing the model lots of examples of how to reason, usually from human experts or maybe a bigger model. Think worked out math problem.
Okay, so learning by example.
Exactly. But getting those high-quality examples, the expert demonstrations, can be super expensive and take a lot of time. Plus, there's always the risk the model just learns to copy the steps parrot fashion.
Mimicking the surface structure without really getting it.
Precisely. Like learning the dance moves without hearing the music.
Okay, so how does RL offer a different path?
With RL, the model learns more directly from feedback. It tries things out, and if it gets the right answer or follows a sound logical path, it gets a reward.
Learning by trial and error, guided by rewards.
Yeah. This can encourage the model to explore different ways of reasoning and potentially find more robust strategies. The catch has always been that RL pipelines generating lots of attempts, checking them, tend to chew up a lot of computational resources.
Which brings us neatly back to Tina and their tiny approach. They specifically chose that 1.5 billion parameter DeepSeek R1 Distill-Quinn model. Why that one?
That seems like a smart strategic move. That particular model, because of how it was trained and distilled, likely starts with a bit more innate reasoning ability than other models its size.
So a stronger starting point.
Kinda, yeah. It means when they apply their RL technique, the effect is clearer. You can better isolate what the RL and LoRi are actually contributing, rather than starting from absolute scratch on reasoning.
Makes sense. Get a clearer signal.
Exactly. And, practically speaking, using a smaller model just makes the whole research process way cheaper and faster. It opens the door for more labs, more researchers to actually try these things out.
Lowering the barrier to entry. Now, let's talk LoRa, low-rank adaptation. For a technical audience who might know of it but haven't used it much, can you break down what it is and why it's such a good fit here?
Sure. So, LoRa is all about efficiency. Instead of tweaking all the billions of parameters in a big pre-trained model when you fine-tune it for a new task,
which is computationally heavy.
Right. LoRa freezes those original weights. Then it injects these small, extra sets of trainable parameters, think of them as low-rank matrices, into some of the model layers. You only train these new, much smaller sets of parameters.
Okay, so you're adapting the model's behavior without retraining the whole thing.
Exactly. You get the adaptation you need, but with way less compute and memory. And what seems really cool here, especially for reasoning, is how efficient LoRa is at picking up formats.
Formats?
Yeah, the hypothesis is that the RL rewards specific output structures, like step-by-step thought processes. LoRa seems great at learning these structural patterns really quickly with just those small parameter changes without messing up the knowledge the base model already has.
So it learns the how of reasoning presentation, leveraging the what it already knows, like teaching an expert a better way to structure their arguments.
That's a great analogy. And it gives you modularity, too. You can basically switch the reasoning behavior on or off by just adding or removing the LoRa adapter. No need for multiple copies of the full model.
Very neat. Okay, the paper talks about the surprising effectiveness of efficient RL reasoning, pointing to Figure 1 and Table 3. What really stood out to you in those results?
The big thing is just how well these TINA models do compared to baselines. We're talking models fine-tuned with this cheap LoRa RL method, often matching and sometimes even beating models that got the full, expensive, all-parameter training treatment on the exact same base model.
Wow, okay, so efficiency and performance.
Right. Figure 1 shows this visually similar reasoning scores, but achieved with way less data, compute, and time.
And Table 3 gets specific, right? Benchmarks like AMT24, AMC23.
Yeah, on AME24, the best TINA model gets that 43.33% pass at one score. That's a solid jump over the baseline. And you see similar stories across Math 500, GPQA, Minerva. These are challenging reasoning datasets.
And often achieved quickly, too, you said.
That's another key point. They often hit these top scores after training for only a fraction of an epoch. It really highlights how fast LoRa seems to adapt the model in this RL context.
Which directly supports their rapid reasoning format adaptation hypothesis, doesn't it? The idea that LoRa is just really good at picking up the rewarded structure.
Absolutely. The thinking is RL for reasoning often rewards a specific output style, right? A logical flow, showing your work. LoRa seems perfectly suited to learn that pattern efficiently without needing a massive retraining of the model's core knowledge.
It separates learning the format from learning the facts.
Kind of, yeah. The small models can reason, the large models know more. TINA learns how to express the reasoning effectively.
And this really feeds into their democratizing RL reasoning point. It's not just about getting better results, it's about making it accessible.
Exactly that. Doing this so cheaply. $9 for the best models tuning, maybe $500-ish for all their experiments, and then open sourcing everything. That dramatically lowers the barrier for other researchers to jump in, replicate, and push this forward.
It puts powerful RL techniques within reach. Now, they also place TINA in the context of other work, these open source reasoning replicas in Figure 2. Where does TINA sit in that landscape?
Yeah, Figure 2 shows this explosion of open models trying to match the reasoning skills of things like O1 Preview or DeepSeek R1. You see still SkyT1, SimpleRL, Prime, loads of them.
A busy space.
Very. TINA joins that group, but the key difference, as they point out, is how it's trained. Most of those other models use traditional full-parameter fine-tuning. Expensive.
Whereas TINA uses LoRa.
Right. TINA's parameter-efficient LoRa approach really sets it apart as a much more cost-effective way to get there.
Did they mention other RL methods for reasoning?
Briefly, yeah. They nod to things like using separate reward models like RefD or Refiner or rule-based checks, self-play techniques, inference-aware tuning, and they specifically mention GRPO and Dr. GRPO algorithms since TINA uses something similar to GRPO.
Okay, let's get into the nitty-gritty of the training. How exactly did they build these TINA models?
So they start with that DeepSeek R1 DistillQuinn 1.5B base. Then they apply post-training, but only training LoRa adapters within an RL loop that's based on the GRPO algorithm. The whole setup screams efficiency.
And the training data, did they create new data sets?
No, and this was smart for comparison. They used existing publicly available data sets from the models they were comparing against.
To keep it apples to apples.
Exactly. So TINA still used the same 33K math competition traces as still. TINA DeepScaler used the 40K pairs from DeepScaler for long context math. And the TINA OpenRS models use those smaller, curated data sets from the OpenRS project.
Very careful setup. What about the hardware? That $9 cost implies they weren't using a giant GPU farm.
Definitely not. They used OpenR1 as a base framework, with libraries like Accelerate, Trawl, DeepSpeed Zero, and they managed it all on just 2 NVIDIA L40S GPUs.
2 GPUs.
They did some clever co-location, running the RL training and the VLLM inference needed for generation on the same GPUs, carefully managing the memory. They ballparked the cost around $1 per GPU hour, and apparently a single RL step took less than a minute usually.
That is seriously lean. And Table 1 summarizes the total costs.
Yep. It lays it out clearly. About $9 to reproduce the best TINA model, and around $526 total for all the experiments in the paper. It just hammers home how cost-effective this LoRa-based RL approach is.
Okay, let's pivot to the results in more detail. They started in stage I by reevaluating the baselines. Why bother doing that?
Good question. Comparing results across papers can be really messy, different evaluation setups, different hardware, slightly different inference parameters. It can muddy the waters.
Right, not always comparing like with like.
Exactly. So to create a really solid, fair comparison point, they reran the key baseline models, the original DeepSeek distilled model. Still, open RS models using one consistent methodology, same framework. Lightfall with VLM, same hardware, same settings, zero-shot pass at 1.
Setting a consistent benchmark.
Precisely. Table 2 shows those reevaluated baseline scores. It's crucial groundwork before comparing TINA.
Okay, makes sense. Then stage 2, table 3, that's the main event, the TINA model results. Beyond the top line numbers, what did you take away?
Table 3 is where you really see the LoRa-ARL combo shine. All 5 TINA variants show strong reasoning, average scores mostly between 48% and just over 50%. And importantly, nearly all of them beat their corresponding full parameter trained baselines.
And often with less training, right?
Yeah, that efficiency piece again.
Yeah.
They often hit peak performance way before finishing even one full pass through the training data, sometimes less than 60% of an epoch. TINA OpenRS 2 hit that top average of 50.60% quite quickly.
Impressive efficiency. Okay, stage 3 was the ablation studies in table 4. What were they trying to pick apart there?
Ablations are all about understanding why something works. They systematically tweaked different parts of the TINA setup to see what mattered most.
Like what?
Things like the training dataset size and source. They tried datasets ranging from just 1.4K samples up to nearly 100K. They also played with the learning rate for the LoRa updates, tested different LoRa ranks, how complex the adapters were, and even compared two RL algorithms, GRPO and Dr. GRPO.
Trying to isolate the key ingredients. What were some interesting findings?
One really cool one was about the data. The model trained on the smallest high-quality dataset, TINA OpenRS with about 7K examples, actually got the highest average score.
Seriously, so more data wasn't better?
It suggests quality really trumps quantity here,
Yeah.
at least for this setup. Having the right kind of reasoning examples seems more important than just having tons of examples.
Interesting. What else? Learning rate. LoRa rank.
Learning rate mattered a bit. 1E6 was optimal for one setup, but it wasn't super sensitive. For LoRa rank, the middle ground seen best ranks 8, 16, 32 worked well, with 16 hitting the peak. So you don't necessarily need super complex LoRa adapters. The parameter efficiency holds up.
In the different RL algorithms, GRPO versus Dr. GRPO.
They got similar peak performance with both on TINA OpenRS 3, but Dr. GRPO got there much faster, using less data. So Dr. GRPO seems more sample efficient.
Lots of useful knobs to turn there. Now, the paper really digs into why they think LoRa works so well here, using figures 3 and 4. This less is more idea in figure 3.
Right, figure 3 plots training compute, FLOPs, against the reasoning score. And it's a stark difference. Full parameter training needs way more compute to reach similar scores as TINA.
So TINA gets comparable or better results with massively less compute.
Orders of magnitude less. They even saw cases where more compute with LoRa actually started to hurt performance slightly. It really pushes this idea that targeted adaptation is better than brute force.
Find the sweet spot, don't just scale endlessly.
Exactly. And it ties back to the hypothesis. RL rewards a specific format for reasoning outputs. LoRa learns that format super efficiently, just tweaking things slightly, preserving the base knowledge. It's teaching structure, not reteaching facts.
Which would be way more costly with full updates.
For sure.
And figure 4, this phase transition in LoRa-based RL, what's that showing?
They looked closely at the training dynamics. They noticed that metrics related to the output format, like the reward specifically for correct formatting or the length of the model's output, often showed a sharp change or transition during training.
A turning point in learning the format.
Kind of, yeah. Maybe the format reward peaks or it gets unstable, or the output length hits a minimum. But interestingly, the accuracy reward didn't usually show the same sharp jump at that point.
Okay, so what's the implication?
The key finding was that the best performing checkpoint, the one with the highest reasoning accuracy, almost always occurred right before or around this format transition point.
So LoRa learns the format quickly, which is good. But pushing that format optimization too hard, past that transition point, doesn't necessarily help and might even hurt actual reasoning accuracy.
That seems to be the takeaway. Learning the format is crucial, and LoRa does it efficiently, but just nailing the format isn't the whole story for getting the reasoning right. It reinforces that LoRa's power here is in efficiently learning the necessary form for reasoning.
Fascinating dynamics. Now, no research is perfect. What limitations did the authors themselves point out?
They were upfront about a few things. First, it's a 1.5B parameter model. There might just be a limit, a ceiling, on how complex the reasoning can get compared to, say, a 70B model.
Makes sense. Size might still matter for the hardest problems.
Probably. Second, their main focus was math and formal logic reasoning. How well this transfers to other kinds of reasoning, like common sense or creative problem solving, needs more research.
Domain specificity.
Right. And finally, they kept hyperparameter tuning pretty minimal to keep costs down. So it's possible that with more fine-tuning of learning rates, LoRa, ranks, etc., the performance could be pushed even higher.
Okay, fair points. So let's wrap this up. What's the absolute core message for our listeners, the folks deep in the AI trenches?
I think the main takeaway is that Tina really shows convincingly that using LoRa within an RL framework is a powerful and incredibly efficient way to build reasoning skills into smaller language models.
Competitive reasoning without the supercomputer budget.
Exactly. They've shown it's possible, and by open sourcing it, they've made it much more accessible for others to explore. It really helps democratize research in this area.
So a final thought for you listening. This rapid format adaptation LoRa enables. What are the implications? How can we leverage this efficiency even more? Could we tackle way more complex reasoning? Or maybe adapt those giant models we already have, but much more cheaply?
What are the limits here? How does this interplay between keeping old knowledge and learning new structures really work under the hood with these efficient methods?
Lots to think about. Definitely check out the paper, the code, the models. We'll put the links in the description. Dive in and see what you can build.
Absolutely. Figuring out how to best use techniques like LoRa to build complex skills efficiently, that's going to be huge for making advanced AI more accessible and scalable.